the stress in the bar, we write it as P divided by A0. But now, if you really think about it, this will not be a unique definition, because does the area A0 stay same or does it change when the load is applied? Actually, the area will change. So therefore, when we define it like this, P divided by A0, this is what we call as the engineering stress. And then we define strain. We use the symbol epsilon. And strain is defined as delta upon L, where again L is the undeformed length and this is referred to as the engineering strain, where the length is the undeformed length. Okay. Now, what is we know is that sigma is a function of epsilon. Now, the sort of advantage of expressing it in terms of sigma and epsilon is you realize that sigma tells you the intensity of the force. So therefore, even if the force is 2p or if the area is 2a, then when we write things in terms of sigma and we plot those variables, then we don't have to depend on the exact load. What we are talking of is the intensity of the load. So in some sense, when we study behavior like this, so we see sigma is a function of epsilon and we plot sigma versus epsilon curve for each material. Now, of course, to do this, you will need some sort of an instrumentation, and we will discuss that in a minute. So there are particular tests which you do, and I don't think any of you will be doing any lab in solid mechanics or fluid mechanics, so you will not be able to. There are machines called the universal testing machine, where you have a specimen, which is an elongated specimen. It is through fixtures, it is tied to two ends, and then a tensile load is applied. And you have done that in which in material science you have already done that. Okay. So as the load is applied, then you also see how much the length changes, and you record that, and you get graph of sigma versus epsilon. Okay. Now this is when the area. Now, does the stress stay the same at each element along the axial length? Let us say if this distance is x, does sigma change with x or is it constant? With x. Now, how will we find out that? So, suppose I have to find sigma at a particular x. I will make a cut section. At the cut section, so suppose I have to find this. So, what I am going to do is I cut a section here and then I draw a free body diagram. I have the load P here. So, then if this load is F, which I do not know, then when I apply my equation of statics, what do I get? F must be equal to P. Assuming the mass is negligible. So here yeah, you're right. Sometimes the P is only because of weight. But we are assuming the mass is negligible. P is very large compared to the mass. Rather, it should be weight, not mass. Okay. So neglecting the weight, so then F is equal to P. So therefore, the stress will be the same if the area is the same. Isn't it? Now, if we have a variable area, then how do we define these things? So let's look at a case like this. A horizontal version. We apply a load P. Area is a function of x. Then we look at an so initially this is a variable area, length, rod or whatever, and we take an element at a distance x whose length is delta x. This is the undeformed length, and after the deformation, the x portion becomes x plus delta, and the delta x becomes delta x plus delta delta. So then the strain would be defined as the change in length of that particular section divided by the original length. So delta delta by delta x, and in the limit delta x goes to 0, this will become d delta by dx. Okay. So this is how you define it when you have a variable. Now, if we look at the SI units, and I didn't even talk of, we have had a full discussion, lectures on stress, but we didn't even talk about the units of stress. So that, of course, but is something which is quite straightforward. If we look in SI units, the units of stress will be that of dimension of force divided by area. So in SI unit, this would be newtons per meter square. And this is also referred to as Pascal. Now in solid mechanics, what you'll find is that typical orders of unit of stresses which you will apply to get appreciable strain will be megapascal, particularly if the material is something like steel or aluminium. And megapascal means we are talking of, and we also have gigapascal, which is 10 to the power of 9 Pascal. So these would be the units of stress. What will be the unit of strain? Strain is dimensionless. Because it's length over length. But in some problems, you will find they will state that strain is something micro, or let's say 10 micro. The word micro would be written. What's the meaning of micro? It's multiplied by -3. Micro is always 10 to the power of -3. So -6, micro, nano, -6, okay. So that would be equal to, एक मिनट, okay, yeah, ठीक है. So it's -6, okay. So that is what micro would be. So that would mean that that means you have to multiply it by 10 to the power of -6. Otherwise, in problems you may find it written as inches by inches, or centimeters by centimeters, or meters by meters. It doesn't matter, that would be dimensionless. But if micro is written, then you have to multiply it by -6. Now another thing is, when you solve problems, then the answers have to be given So, for example, you work out an answer and it comes out as 3.2348 Pascal. Then you have to write it as 3.23 Pascal. Use only the first three significant digits if it is not starting with 1. And if it is something like 1 point, now here you count 4 digits. So always start from the first non-zero digit. If there are zeros in front, you don't count them. And so if it is 1.00896, that's what your calculator tells you, then you have to give it as 1.009. Okay? So just round it up, and so 3 or 4 significant digits, depending on whether you are starting with 1 or not. Because typically that would be more than that, your instrument will not be able to handle that. So that's the order of error of the instrumentation. So there's no point writing 10 digit answers, etc. Homeworks भी पिक कर लेता, वो चेयर यहाँ ले आया. अच्छा, ओके, इम्पोर्टेंट है. होमवर्क्स का आएगा तो प्रकाश पिक कर लो तुम सबसे. कर लिया, ओके. Okay. So now, how do we find these stress versus strain? And as we said, that these we use what are called tensile tests. So we plot sigma versus epsilon, and the typical behavior looks like this. So this is if the material is in compression, these are typical sigma versus epsilon curves. And for a brittle material, you keep on applying, increasing the stress, you have a curve like this, and then suddenly the material will rupture. So in a brittle material, in fact, it doesn't even go that much in the flat part, but it suddenly ruptures. So that is how a brittle material behaves. But in a ductile material, the behavior is a bit different. In a ductile material, what you find is as we increase the stress, uh, the strain increases, and then there is a point which is termed as the yield point, where when you the material sort of starts to sort of flow a bit. That is what is called the yield point. And then there's a region, this is called the region of strain hardening, where the material stress keeps on increasing. And then comes this point, the highest point, which is called sigma u, or ultimate stress, after which suddenly then the stress decreases. We have more of flow of the material, and that is when you find the area also changes quite a lot. After ultimate stress, we have a sudden reduction of area, and then the material will break. Pardon? Yeah. So again, now which stress are we talking of? And that is what we talk of is, and that's what I was coming to, that what we have is, so therefore in cases like this, we also have another stress, or we define what is, so what we are plotting here is engineering stress. So that is why it behaves like this. But we can define what's called as true stress, which is equal to P divided by A, and this is area at the load stage and not A0. So this is what we call as true stress, where we take into account the change of area. Okay. And we also have, based on true stress, true strain epsilon, which is equal to sum of delta epsilon, which will be equal to summation of delta L over L, and this we can therefore write it as so if at each length, if we look at that instantaneous length and find the delta L at that length, and we sum up all this, so that will become basically, finally, if the length at yield or at the breaking point is L, so then log of L by L0 will give us what is called as the true strain. Now, whether we have a brittle material or a tensile material, there is an initial portion where the stress behaves linearly with strain. And this relation, by what law do we know as? We know this as Hooke's law, which you also have probably seen in your high school physics. So this gives us what is Hooke's law, and we define modulus of elasticity E as sigma is equal to E is called the modulus of elasticity or Young's modulus. Now, epsilon is equal to sigma upon E. So, that means delta upon L is equal to P upon AE, and this gives us a relation delta is equal to PL upon AE. So, this is the basic relation which then Young's law, basically Young's modulus gives us, or is it called the Young's law? I don't even know that. So, this is what we have. Now, of course, so you can use this, for example, even if you have, or sorry, let us say if there are multiple loads being applied on this multi area bar. So, this is basically, let us say here the area is A1, the area here is A2, and the area here is A3. So, now if you have to find the extension at any stage, so what you do is you make a cut section, you cut it either from the top or from the bottom. Of course, here now the advantage is if you cut from the bottom, then you will be able to find out all the forces, because there is no, if you cut from the top, then you will have to first find the force on the force and the moment at the reaction supports. So, and then you will find delta at each stage. So, eventual extension will be sum of all the forces by AE. Okay. So, this is what we have. So, if I, let me just, if I make a cut section here, if this is L1, so the extension of this part will be given by P1 L1 over A1 E1, and similarly then I can cut on at different sections, and what I will eventually get is that delta will be equal to summation over I Pi Li. So, this is when you have multiple discrete loads, and when we have, if we have a single load P on variable area Ax, then delta will be equal to integral of if the only change is the area, the load stays the same. So, then Pi will become P, L will become delta x, and A and E, it's the same material. So, A is a function of x. So, we'll get integral P dx upon AE. No, EI is if they are different materials. Each part may be different material. So that's why I have used EI. So now given these load deformations, now when we look at problems, see, we have seen problems which are statically determinate. What do we mean by statically determinate? We can find all the forces in all the members with just statics. So there, in those problems, these relations will give us the deformations. We'll be able to find the force in each member. So given the property of that material, we will be able to find how much it deforms. But then there are certain problems which are statically indeterminate. In those problems, what will happen is that there will be a constraint which the geometry will offer. And we'll have a look at these. So there what we'll do is, we'll find the relation delta is equal to PL upon AE, and then try to sort of match the geometrical deformations compatibility with these relations, and that is how we'll be able to solve statically indeterminate problems. And let's see how. So statically determinate so here we can solve the forces in members in indeterminate problems. The number of equations is not enough to solve the unknown reactions. For example, if I look at this, a simple rod being supported on the wall with a pin. Now this one is a statically determinate problem because at B a load P is applied. So now I can find the reaction at point A. But suppose if I have a problem like this, where the rod is connected with two pins and a load is applied somewhere in the middle of the rod, an external force P is applied. Now here I will not be able to find RA and RB just by using statics, because all I will have is sigma Fy is equal to 0. Sum of moments is equal to 0 is not going to give me anything. So therefore, I will not be able to find Ay and By using this. Okay. But then in the first problem, what is going to happen is, what is the length delta, what is the extension delta at B? That will be equal to P times L upon AE. In the second problem, what is delta at B? That has to be 0. So that is the fact which you will use, which is what I mean by geometric compatibility. Geometry will tell you that delta at B is equal to 0. So then I will find delta at B in terms of RA and RB. Okay. And then I will also have a relation, RA and RB are related to P. So then that is how I will be able to solve the reactions at A and B, using basically the material properties. So there are, in the statically indeterminate problems, we need three things. One, equation of statics. Two, the geometric compatibility equations. and 3, the force deformation equations. And these 3 principles we will be using throughout in the solid mechanics course. So let's write these down. So to solve for problems, and if the problem is statically determinate, then you will be able to get the deformation using the deformation relations. So to solve for problems, first we will use equation of statics, that is sum of forces is equal to 0, sum of moments about one point is equal to 0. B we will be looking at the geometric compatibility. In certain cases, if it's a straight member and if the member is pulled down by one side, then on the other side it has to go up, and then deflections have to follow similar triangle type of thing, as again we will see these. So geometric compatibility has to be seen, and the third thing then we will have to use is the stress strain or constitutive equations. And using these 3 principles, we will then be able to solve even the reactions at statically indeterminate problems. Okay. Let us look at an example. So we'll use we have a cylindrical bar of area A1 and elasticity E1, and this is covered by an outer tube of area A2 and elasticity E2. So you can think of this as a composite type of bar. Inner part is a circular cylinder and it is covered with an outer tube. So think of it like a wire. In a wire, what do you have? You have a copper part inside and outside is a rubber part which is protecting the wire. So it's something like this. So and here what we are doing is we apply, so this is the outer tube. A force P is being applied totally, so it's covered with some sort of a cover and a force P is applied there. And we want to find the stresses in the bar. So now if I draw the free body diagram of the inner cylinder, then this is what I am going to get, that there is a force P1. I do not know how this force P is divided on the inner cylinder and the outer cylinder. So in that sense, this is a statically indeterminate problem. I know the total force is P, but how much of this P is going on the inner cylinder, we don't know. How much of the P is going on the outer tube, we don't know. So if I draw the free body diagram of the inner cylinder, I get it like this, and free body diagram of the tube gives me a load P2 like this. And what we'll have is, this is what statics tells me, that the sum of P1 and P2 has to be equal to P. Okay. Now, because this is a compressive force, so basically this whole structure is going to decrease in length slightly. Okay. Now, what does, let the deflection, let delta 1 be the compression in 1 and delta 2 be the compression in 2. So, the first part which I said here, equation of statics just give me P1 plus P2 is equal to P. This is what I get from statics. Now, if delta 1 and delta 2 are compressions in 1 and 2, and if basically and now using this you can find P1 and P2. Okay. So, this is how we can then solve statically indeterminate problems. There is another method which is used, and this is called the method of superposition. Now, in method of superposition we realize that stress strain relations are linear. So, if you have a linear equation and then you can superpose solutions. For example, if you have an equation y is equal to f of x and this is a linear equation, there is a solution y1 and there is another solution y2, then y1 plus y2 will also be a solution. In linear equations we can do superpositions. So, here in such problems what we do is, if in such problems there are more supports than those a problem becomes statically indeterminate if you have extra supports. If the supports are just enough, then it will be statically determinate. But you put extra supports. So, for example, you have a log lying on two ends. That is a statically determinate problem. You put a third support in the middle or somewhere else. That makes it statically indeterminate because you have put an extra support. The extra support gives an extra force. So, that is what makes it statically indeterminate. So, what we do is we designate one load as redundant and eliminate so one of the load which comes from that support, we determine it, we call it as indeterminate. So let's look at a case like this. For example, let's say this P is known. The reactions are L1 and L2, and there's some, I've shown this P so that, or even if the P is 0, then all you get is L1 plus L2 is 0, but you don't get the value of L1. So this you can write it as equal to L1 and P plus so we remove one of the supports, call it as redundant, and do the other one. Now here, let the deformation which comes be delta 1 in one case and delta 2 in the other case, and then we can superpose the two, and the relation between delta 1 plus delta 2 will come from the problem, from the geometric compatibility. So this way then we can solve the problem by method of superposition. Okay. Then there is, so again examples of this you will see in the tutorial sheet which will follow. This week's tutorial sheet, Friday you had a tutorial or no? So you did problems of stress transformation, isn't it? So similarly now this whole week you will see stress transformation till Thursday class. Friday onwards we will do problems of chapter 1, which is not these, the last class problems. This will come in the week after this one. But you can still go through the book. See, now since I am following at least this part, I am following a textbook. This will be Tute 4 now. The Tute 2 is stress transformation. Tute 3 will be chapter 1. So this will be Tute 4. Okay? No, Thursday, but Thursday की इस बार एक okay. So Thursday. Acha, because we didn't have the first Thursday. So thoda sa I'll ask the Thursday teacher to cover up maybe. Or I don't know if the Thursday people are you free on Tuesdays or some other day? नहीं सभी होगा ठीक है तो I'll ask the teacher to cover up. But they are straight right now we have not got into a difficult portion of the course. So you can, I have already put up all the up to Tute 3 and I'll put up Tute 4 also very soon, today itself. Because next 2 days I'll not be here. As we said, next Thursday we are not having a class. So next class will be on Monday only. Now there is another type of strain which comes without a stress, and that is because of temperature change. If suppose I have a material, I heat it up then I find there is a change of length. But it is not accompanied by any stress like we had, that if you apply a stress, there is a strain. This thermal strain is coming because you heat up the material, not because of a stress. So now let's try to see what happens when there is a temperature change. So suppose I have a bar like this and I heat it up. Now because of the heat, so if you there is a change of length, and this change of length, which let me call it as delta t, is given as alpha times delta t times L, where alpha is called the coefficient of thermal expansion, and the strain because of this will be equal to alpha times delta t. Now as such, there is no stress associated with epsilon t. But in this case, suppose here I have this geometry. Initially, let's assume that it is just snugly fit rod, so there are no stresses. But if I heat it up, then what will happen? Its length will increase, but the length is not allowed to increase because of this thing. So therefore, stresses will come in. And because of the stress, you can think of what is the load P, which is coming in because of the heat. And that load we will get from the relation delta is equal to PL upon A. So because delta is not allowed to change, so whatever this delta is coming will be equal to PL upon A. So you can get you can relate this. So if now so what you will get here is alpha delta t times L this I should say uh, delta due to P1 and this is delta due to the temperature. The change of length due to temperature will be alpha delta T times L. The change in delta due to the load will be equal to P1 L upon AE, and the sum of these two must be equal to 0. So therefore, using this you can get the value of P. So this load P1 is equal to minus A E alpha delta T. So, this is what we do in when there are thermal stresses, then we have to account for these using this. Now, we also have to, these are cases when there was just a single stress. What you should also realize is that these stresses which we have found, these are on a face which is perpendicular to the force being applied. Does this mean that there are no shear stresses in this whole bar? Now, what you have to think of is, so this is the face which I have looked at, and here if the force is P, you have sigma is equal to P upon A. And actually on this face, the shear stress is 0. But if I look at section AA, on this section AA, the force perpendicular to the area, that will be sigma, and tau will be the force here, and on this section for the same loading, tau will not be 0. And how do we know this? Let us just plot a Mohr circle. Okay. So, now for this loading, how will the Mohr circle look? Sigma xx is equal to P by A, sigma y is 0, and there is no tau. So, the 2 points we start with on the Mohr circle are basically sigma, P by A and 0, and then what I have to do is, I have to draw circle here. So, this is the actual loading for a uniaxial stress. This is how the loading looks like. And what it tells me is, so these are my 2 points A and B for the original stress. But, so where will the maximum shear stress come? 90 degrees in the Mohr circle. So, in the actual picture, it will be at an angle of 45 degrees. So, the maximum shear stress will be at 45 degrees, and so that we have already seen. So, therefore, in fact, we saw the other thing for the brittle material when I broke the chalk. But now using this, suppose we know, we saw, you have seen this test, some of you, did the energy people also do the material science course? You are doing it. So, you will see this experiment, you must have done it, where you put a ductile material under tension. So, ductile material under tension, the state of stress is given by this Mohr circle. But the ductile material fails under shear stress. It does not fail under tensile stress. So, therefore, for the ductile material to fail, where is the maximum shear stress? At an angle of 45 degrees. So, therefore, that is why at the point where the breaking occurs, if you will find the necking, at that point the angle is 45 degrees. It is not a straight cut. For a chalk type of material, brittle material you pull, it will cut straight. But a ductile material, the failure will be because of shear stress, so therefore it will be at an angle of 45 degrees from the original. So, you will be able to see that, and that is why I taught Mohr circle before, because even for this loading there is a shear stress. It is not that shear stress is not there, but it is at another plane. What we are finding using all these analyses will only be tensile stresses, but a shear stress corresponds, and that comes at an angle of 45 degrees. Okay? Now, we have another term and called Poisson's ratio. We have talked about Young's modulus for a material. Now, let's look at a bar like this. This is fitted on a wall. The force P is applied. This is the x direction. And let this be the y direction. Sigma x is equal to P upon A. Now, now we are pulling the material in the x direction. So, now notice very subtly I have introduced a subscript with epsilon to tell me the direction. In the x direction, the strain is given as sigma x upon E. This is the loading which we saw. Now, the question I am asking is the strain in the y direction and the z direction 0 or not? And as most of you feel that this is not 0, because answer to this is no. Why? Because elongation in x is accompanied by contraction in y and z directions. Now, if there is a term which we use, which also came in the fourth problem which you are not supposed to submit, isotropic. If properties do not depend on the directions, then what do you expect will happen to epsilon y and epsilon z? The loads in the y and z directions are the same. The loading is only applied on z direction. So, if the material is isotropic, you will expect epsilon y and epsilon z to be equal. For an isotropic material is one. So, let us first define isotropic material is the one where properties for example, you look at a block of iron or any material, as whichever direction you go, you do not expect the properties to change. But an example of a material which is not isotropic is wood. In wood you have grains, and so the property along the grains and the property across the grains will not be the same. So, a material like wood will not be isotropic. Sometimes to make the material strong in a particular direction, you add rods or very thin rods all along the same direction. Such a material will not be isotropic. But sometimes to make it strong in the same thing, you mix things, like for example in concrete, you mix stones with cement or things like that, or then it is isotropic in a broad sense, unless if you go to very microscopic scales. So if things are all well mixed up, the material is isotropic. But if you have properties which are varying along a direction, then it is not isotropic. So in isotropic material, expect epsilon y is equal to epsilon z for above case. And what you will find is epsilon y is equal to epsilon z, and generally this will be less than 0. Now we called epsilon x as the axial stress and epsilon y and epsilon z, axial strain, and these as the lateral strain. So then these are names given to this, and for any material what we find is that we can define a quantity called Poisson's ratio, which we use a signal nu. This is equal to minus of lateral strain divided by the axial strain. So in this example, nu will be equal to minus of epsilon y by epsilon x, or minus of epsilon z by epsilon x. Now we also know epsilon x is equal to sigma x upon E. So epsilon y and epsilon z, the two lateral strains, these will be equal to minus nu times sigma x upon E. And this value of Poisson's ratio is normally fixed for a material, and actually what you find is that volume will not be conserved. See, because basically from here you can get the volume of the material now in the new loading. See, the length has increased in the x direction by delta x. It has decreased in the y and z directions by delta y and delta z. So the new volume will be equal to L plus delta multiplied by Lx plus delta x multiplied by Ly plus delta y, algebraic delta y, multiplied by Lz plus delta z. So you will have a new volume, and what you find is actually the volume is not conserved except for a particular value of Poisson's ratio. So only in general we expect, but the deviations are very small because epsilons are in sigma, this modulus of elasticity is large. So therefore you find this. So in general, volume of the solid is not conserved. This is one thing, and secondly, there are some materials where the way we have defined nu, we have used a negative sign in the definition, which means we are expecting that if we are pulling in one direction, there is contraction in the other two. But you still find some materials where Poisson's ratio is less than 0. That means you pull in one direction and they will also increase in the other directions. So there are some materials which you will also find this. Now in the next class, we will look at multi-axial loading. Once again, we will look at a case where loading will only be normal to the surface, but we will look at the loading in all the three directions. That means the load in the x, y and z directions. We will look at the multi-axial loading, and there I will also talk a bit about how to draw the Mohr circle for a three-dimensional case. We have looked only at a planar case. But I think one take home which I want you to have is that for each loading, whenever we draw the simplest loading first. But at least in your mind, you should think of the Mohr circle for that loading, so that you know what is happening in the other planes and where the shear is also maximum, or where we have a loading where there is only shear, then in which directions do we have a tensile load. Okay, thank you. So now we will meet on next Monday. हाँ
आज स्टार्ट किए थे वो
हाँ ओके ये थोड़ा मिस हो गया कहाँ आ गया होगा मतलब फिगर तो आ गई होगी थोड़ा सा लेक्चर से